Hi, I'm David Bendori. I'm the engineering manager for Tekton. I have been at Google since 2015, and today I'm here to talk with you about binary authorization for Borg. This is an internal system that we use at Google to verify code provenance and to implement code identity. And presenting today alongside me will be my colleague, Christy Warwick. Christy, do you want to introduce yourself?
Sure. Hi, everybody. I'm Christy Warwick. I'm a software engineer at Google where I lead Tekton and Secure CI/CD.
So we're going to start the presentation with me focusing mostly on Google's internal processes. I will then turn the floor over to Christy, who will talk about similar tools for Tekton and open source. Then we'll come back to me. I'll provide a demo of binary authorization running on Google Cloud Platform itself. Google has released a white paper on binary authorization for Borg, in which we describe Google's code review process and the way we gather provenance and the need for enforcement mechanisms. And that's really what I'm going to be talking about today. So the context we're talking about here is minimizing insider risk. And our goal is to prevent a nefarious actor from infiltrating our own build and deploy processes to distribute malicious code. There are times when our services and our personnel have access to user data, and we interact with that user data in the following ways. So first, we interact with user data as end users. I am a personal user of Gmail. I use that outside of my role as a Google software engineering manager. And of course, I might access my Gmail as an end user from inside of Google. That kind of access is obviously completely appropriate. The second way I might access user data while I'm at Google is as part of my role as a software engineer or engineering manager. You can think of the example of a Google Cloud customer who gets in touch with us, asks us to help debug something that isn't behaving as expected. And with that customer's permission, we might access some set of their customer user data as part of the debugging process. Finally, the third way is we access user data as part of a service programmatically. This is where software running in our production environment has access to user data in order to perform the functions that software is designed to perform on behalf of our customers. Our goal is to minimize the threat model presented by insider risk of inappropriate programmatic access to customer data. And we focus on that by trying to prevent a malicious insider from inappropriate access. That will also prevent an external actor who has infiltrated from gaining access that's inappropriate. So to understand this, we need to understand the life of a production job at Google. At Google, our production jobs run on a system called Borg. There's actually a white paper out on that as well if you want to learn more about Borg. Production jobs at Google are required to meet certain standards in order to be deployed in our production environment and gain access to customer data. The code has to be authored, a code review is required, and the code ultimately is submitted to our repository. A build system then automates build and packaging of the code for deployment, and the artifacts created by the build system are signed. Next, the job is deployed to production by a user who's authorized to create such a deployment. That deployment goes out to a secure production identity. And finally, the job runs in production as that production identity. And it's that production identity that has authorization to access the user data. And so a lot of verification happens in that process. The verification mechanism for this is binary authorization for Borg, or I'll just call it binary authorization as we go through here. It's a deploy time enforcement of code, build, and deploy policies, those same policies that I just described. It checks the signatures of the deployed artifacts, and it enforces policies. It ensures that the code running in production has been through a code review. As one example, it has been through testing. It has been signed off by the right parties. Let me give some examples of those binary authorization checks. There are a variety of deploy time checks that take place. Some examples. Is the binary built from checked-in code? Is it built verifiably? Is the binary built from tested code? Is it built from code that was intended to be used in the deployment as part of this particular production system? As the binary authorization system asks these questions, it has various enforcement modes in order to enforce these policies. One is deploy time enforcement. So at the time that an engineer tries to deploy an artifact into production, binary authorization will simply block a job from deploying that code if it doesn't meet the policy standard. Another enforcement mode is deploy time audit. This is where we go into an audit mode where we watch the software in production, we report on violations, but we do not actually block the software from running. And the last mode is called continuous verification. This is where the binary authorization system continuously watches production and confirms that policies continue to be enforced over time. These last two enforcement modes are critical for our ability to roll out new policies. You can imagine that when a new policy comes along, we don't want to turn it off across our production fleet and possibly block a whole lot of production jobs from appropriate access. Instead, we start out in audit mode. We record where that access is going place, where that access is taking place. We verify that it's correct. And then ultimately, we turn on a continuous verification mode. Binary authorization provides several security benefits. The primary one is reduced insider risk, and it was developed to prevent any single individual from obtaining unauthorized programmatic access to user data. It makes it difficult for a single engineer or an attacker who gains an engineer's credentials to access sensitive data inappropriately and without detection. Another aspect is robust code identity. Borg jobs run in production as an identity. Those identities are used by various services, and binary authorization enables us to verify proper authorization before granting access to any data. And finally, binary authorization simplifies compliance. The continuous enforcement mode means that we know that policies are being upheld at all times. And so when a compliance audit comes along, we know a priori what policies we are in conformance with. This all sounds like a terrific system, but how do you actually adapt such a system? Well, there's a tactical approach to that. One piece of that at Google was working toward a homogeneous, containerized continuous delivery pipeline. That enabled us to have a single pipeline to look at for policy enforcement. We determined our goals and defined policies based on those requirements, and we tried to enforce those policies very early in the development cycle. This is part of a shift left mentality on security. Finally, we put a lot of consideration into determining how to onboard existing service owners. Finding a handful of service owners who would see the immediate benefits was critical to that. And we enlisted change agents in those teams and across other teams at Google before creating a Google-wide mandate for binary authorization. Having figured all of that out, we also had to figure out how to manage third-party code. This comes into play much more strongly in an open source world where most open source systems are dependent on a variety of other open source packages. At this point in the presentation, I'm going to hand off to Christy, who's going to pivot from the internal binary authorization that I just discussed to our tooling in the cloud that enables binary authorization with OSS tooling like Tekton.
Thanks, David. So you might be thinking, that seems really handy, but binary authorization for Borg is an internal system used at Google. If I wanted to use something like this, would I have to start from scratch? Fortunately, no. On Google Cloud, we have a product called Binary Authorization that is inspired by its internal counterpart. It's a deploy time security control that ensures that only trusted container images are deployed on Google Kubernetes Engine or Cloud Run. Binary authorization lets you require that images are signed by trusted authorities during the development process, and it enforces signature validation during deployment. Binary authorization has many of the same kinds of controls that we've just discussed. It supports policies such as signature-based verification and image allow listing. With the allow listing, you can designate allowed images by repository, by path, or by a specific set of image digests. And you can set these policies at the project level and at the cluster level. There's also break glass functionality with audit logging, which you can use if you need to make deployments in emergency situations. The key to making this all work is to be producing these signatures, attestations, and provenance as part of your build lifecycle. As your CI/CD platforms transform your source code into production artifacts, such as container images, something needs to be creating that trusted provenance that contains the data that binary authorization policies will act on. In this talk, we want to highlight how this is possible using Tekton and how you can use Tekton with GCP's binary authorization. As you may know, the main component of Tekton is Tekton pipelines, which execute CI/CD workloads as pipeline runs and task runs. The optional Tekton chains component integrates seamlessly with Tekton pipelines to automatically generate standardized SALSA provenance for container images with support for more artifact types currently in progress. So, what is SALSA? It stands for Supply Chain Levels for Software Artifacts, and it defines a series of levels that anybody building software can comply with to provide increased confidence and security. It has been intentionally structured so that you can see immediate improvements in your processes without having to perfect everything at once. You can start at SALSA Level 1, which is relatively easy to achieve, and then incrementally work your way through the levels, benefiting from each upgrade as you proceed. Tekton is working toward providing users with all the features they need to comply with the SALSA levels all the way up to level 4. At the moment, Tekton users can achieve SALSA level 2, and features are in progress to provide level 3 and 4 assurances as well. And this includes some cutting-edge CD features, for example, hermetic execution. In addition to defining these levels, SALSA also defines a standard format for artifact provenance. And to generate this provenance, Tekton uses Tekton chains. Tekton chains produces SALSA provenance by observing the execution of task runs and pipeline runs. It uses type hinting to infer when artifacts are created and generates provenance for those artifacts. It can store the provenance in a variety of locations. For our purposes today, we want to highlight that it can store provenance in GCP's container analysis service via that service's Grafeus interface. This means that by installing and configuring Tekton chains alongside Tekton pipelines, you can start automatically creating provenance in GCP that can be used with binary authorization to gate deployments to GKE and Cloud Run. In the following demo, we're going to show you how you can gate deployments to GKE using images and provenance generated by Tekton. In the setup for the demo, a Tekton task run has already been used to build an image called allow, and the task run has pushed it to the artifact registry. Tekton chains was running in the cluster, so when the image was created, Tekton chains observed that this happened and generated provenance for the image in GCP's container analysis service. Meanwhile, a potentially malicious actor, David, has also built and pushed an image called deny to the same artifact registry. But instead of complying with production policies and using the Tekton cluster, he decided to build and push it from his own machine, so no provenance was generated for it. Let's see what happens when these images are used as part of GKE deployments in a cluster protected by binary authorization.
My name is David Bendori. I'm the engineering manager for the Tekton team at Google, and I'm going to give a demo today of our binary authorization offering on Google Cloud Platform, which is our externalization of binary authorization for Borg. Everything you're going to see in this demo today is available in open source. If you go over to github.com/Bendori, you'll see that I have a repository there called Tekton on GCP. That repository contains scripts that can be used to set up a GCP project exactly like this one. These are the scripts that I used to set up and even run this demo. And that will enable you to set up a similar pair of clusters in a Google Cloud project and play with Tekton chains and attestations yourself. So here I'm at my command line. I've set up my GCP project already. And as you can see here, I have got 2 Docker images already pushed to my repository. The repository is named my repo. One is cleverly named allow, and the other is cleverly named deny. I used a Tekton task run to build an image called allow. That image was signed by Tekton chains, which also created an attestation attesting to the provenance of the image. In contrast, I built the deny image using a local Docker build, and pushed that image to the repository. It has no associated provenance or attestation. I'm going to now create deployments for each of these on my Kubernetes cluster. One deployment for the allow image, which I will call allowed, and a second deployment for the deny image, which cleverly I will name denied. Now, when I look to see if these deployments are in place, what I find is that the allowed deployment is ready, it's up to date and available, whereas the denied deployment is not. The reason for this is binary authorization. If I look at the events on my Kubernetes cluster, I see events for pulling and pulled the allow image, whereas there's an error for setting up the denied deployment with the deny image, which says there that no attestations were found that were valid and signed by a key trusted by the attestor. Let's go have a look at that in the Google Cloud Console. So here we're in the Google Cloud Console for the same project. And if I go and look at my Kubernetes clusters, I have two clusters up. One is called Prod, one is called Tekton. The Tekton cluster is where I built these images using Tekton. Here's the Prod cluster. And you can see on the Prod cluster, if I scroll down to the security section, I have binary authorization enabled. Let's go look at the settings for that binary authorization. It's under the security area, cleverly named binary authorization. And when we look there, we see that we have a policy in place for this project. The policy for GKE cluster US Central 1.prod, which is our production cluster, says that we will only allow deployments of images that have been approved by all of the following attestors, and it lists the attestor that we used to attest to our image. If we go look at the workloads on the cluster itself, we see our two deployments here as two workloads. One is the allowed image, which was allowed to be deployed. The other is denied image, where you can read the error there. At the end of the error, the last line, well, starting at the penultimate line, no attestations found that were valid and signed by a key trusted by the attestor. This deny image that I tried to deploy was built by a nefarious developer in this case, who did not use our standard build chain to build it, and so did not have the attestation in place certifying that this image was deployable in our production environment, in contrast to the allow image, which was built using our standard Tekton toolchain and therefore had the needed attestation in place.
So in conclusion, implementing a deploy time enforcement check as part of Google's containerized infrastructure and CI/CD process has enabled us to verify that code and configuration we deploy meet our standards for security. This is a critical control used to limit the ability of potentially malicious insiders to run unauthorized jobs that could access user data. Adopting binary authorization for Borg has allowed Google to reduce insider risk, prevent possible attacks, and also support the uniformity of our production systems. Binary authorization in Google Cloud brings this power to GKE and Cloud Run, and you can use it with Tekton by having Tekton chains generate SALSA attestations in GCP's container analysis. To learn more about binary authorization for Borg, binary authorization on Google Cloud, and container security, check out these links. And that's all we have for you today. Thank you very much.